TP to. Great. So we're very happy to have for our last talk today Yifan Wang from NYU. So he's done a lot of work on topological defects, defect RG flows, anomalies, I think even some 40n equals 2 SCFT stuff back in the day. And yeah, so please take it away.
Yeah, thank you, Matt. I want to first thank the organizers for putting together this nice conference. Unfortunately, we cannot have it in person, but it's still a pleasure to present some recent work of mine and my collaborators virtually. So today I'll be talking about defects and anomalies in quantum field theory. I will start by introducing defects. So as this is probably all kind of familiar to most of the participants, that is, defects are quite ubiquitous in quantum systems, and they also have very precise description in quantum field theory, which capture some long range or continuum behavior of these defects. Some prototypical example of such defects is given by the Kondo effect, which describe magnetic impurities in metal. And in the quantum field theory, this is described by certain defect lines in the SU2 level K WZW model, this old work of Appler and Ludwig. And also defect shows up in high energy physics, describing world lines of heavy charged particles. And in quantum field theory, in this case, given by a gauge theory, these world lines correspond to Wilson, or more generally Wilson-Tooth loops in the gauge theory. And defects also shows up in lattice systems, for example, in condensed matter systems, as boundaries for your lattice system, or more simply a spin chain. And in this case, these interesting defects are described in the continuum limit by certain conformal boundaries, since this is starting from some early work of Carty and Deal. And defects also shows up in string theory, importantly, as D-branes. In this case, if you think about D-branes as boundary, in this case, you should think about D-branes as boundary states for the Will-Tree string theory. And correspondingly, they are described as some two-dimensional Carty states. Again, something that was studied in the early days by Carty. So the defects has a very apart from these examples, defects actually has a very universal descriptions in quantum field theory. They are described in general by extended operators that are defined on a space-time submanifold. So suppose you have a d-dimensional quantum field theory lives on, say, flat space with these coordinates. The defects are extended operators that live on a submanifold, p-dimensional submanifold, which I'll denote by sigma. And I'll denote this, use curly d to denote the defect operator. And roughly speaking, most of the examples of the defects we know fall into two categories, which are not mutually exclusive. So one such category are described by so-called order type defects. This includes the familiar Wilson lines, and they often take the form of the following exponentiated integral, where the exponent is some local integral of some functional that are built out of the bulk quantum fields, which I denote collectively by phi here. So in the case when phi is the gauge field, the gauge invariant exponentiated integral defines the Wilson line. More generally, the disorder type defects, for example, Tooth lines and also vertex twist operators, which are codimension 2 defects, can be defined by imposing a boundary condition for the quantum field in your path integral along the defect locus, which I'll denote by sigma. Okay. But more generally, defects will not have this nice descriptions in terms of elementary quantum fields. Rather, they are characterized by the symmetries that they preserve and the symmetry that break. Importantly, defects, the non-topological defects will break part of the Poincare symmetry of your quantum field theory. In particular, breaks the transverse translation symmetries, and this gives rise to important defect operators known as displacement operator, which will come up later. And more abstractly speaking, in this most general case, the defects are characterized by the correlation functions of local operators in the presence of defects, and and satisfy a bunch of consistency conditions, which takes the form of some generalized bootstrap equations, and that's the most general way we should use to think about defects, especially in quantum field theory that does not have Lagrangian descriptions. It turns out that these defects not only describe a wide range of impurities and boundaries in quantum systems, they're also a very important part of modern notion of quantum field theory. They're dispensable in the following ways. First of all, topological defects, which is a special kinds of defects that are invariant under infinitesimal deformations of the world volume. They give rise to natural generalization of symmetries. For example, higher form symmetries that generalize the usual zero form global symmetries, as well as more exotic generalizations that involve non-invertible symmetries explored in a number of papers. And in particular, the charged objects under these generalized symmetries, in particular, the higher form symmetry, the charged objects under the higher form symmetries are defect operators. Okay, there are, for example, the charged object under the one form symmetries are precisely the Wilson-Tooth lines. And there are important other parameters for phase transitions in gauge theory, for example, the confinement, deconfinement transitions. And the defects, also importantly, they are very sensitive to global structure of the theory, unlike correlation functions of local operators. In particular, there is known that given a set of local operators, there can be distinct extensions of the local operator algebra by defect operators, which give rise to distinct extended quantum field theories. Explicit examples are given in this paper that concerns different four-dimensional gauge theories with the same local operator spectrum, but distinct line operator spectrum. And the study of defect is also a very exciting laboratory for mathematics. For example, in case of the 4D-2D correspondence that involve 4D gauge theories and the total theory on a two-dimensional Riemann surface, if this correspondence is greatly enriched once you incorporate defects and give rise to various interesting developments. And the general picture, the general kind of strategy, one general strategy you can take is always, if you have some correspondence, you can ask what happens when you include defects. And more likely than not, you will find some interesting, you'll have something interesting and rewarding to say. So here is a kind of a big picture that I have in mind when I look at the recent development in defects. So roughly speaking, a lot of recent developments in studying the defects fall into the following subtopics. So I think the central object here is the defect extended operator algebra, by which I mean the spectrum of all these defect operators, together with the correlation functions that involve these defects, as well as local operators. And the inclusion of defects enrich the kind of set of universal observables that we can consider, in particular anomalies. Okay, and in particular in the presence of conformal symmetry, there's this conformal anomaly and also other universal things, universal quantities such as the defect free energy. Really something that Ananda talked about, which plays a role in the entanglement entropy in the presence of the defects. And we'll see that the inclusion of defects enrich such universal quantities. And it turns out that by studying a property of such universal quantities, you can also deduce non-trivial constraints on what kind of defects and what kind of defect dynamics are admissible within the consistency conditions of this defect extended algebra. Okay. And something else is that in the case with additional symmetries like supersymmetry and durability, symmetry in the broad sense, supersymmetry and durability, there are very efficient tools to compute various observables in this defect extended operator algebra using these methods. Okay, and this is something that Charlotte already talked about in the case with that can be applied in the case of 14-4 preambles. Okay. And as I mentioned briefly a couple of slides ago, there's also this important class of defects known as topological defects that give rise to some generalized symmetries. And here, this topological defects, they will furnish some categories. Okay, that's along the line that Ilka talked about. And these categories would act on the full defect extended operator algebra, where the other objects, such as the non-topological defects, will fall into modules of this category. And various features like anomalies and stuff can be captured in principle by studying algebraic properties of these modules. And this is something still to be studied in higher dimensions, but this is something that has been indeed studied extensively in two-dimensional quantum field theories, so especially 2D CFTs, but I will not have time to talk about it here. And another interesting direction is to explore the relation between these defect operators and non-perturbative objects in string theory. Why? Via two routes. One is to explore the connection between the two-dimensional boundaries of two-dimensional quantum field theories with branes in string theory using the Walsh string theory. Okay. Another is to explore the correspondence, the ADS-CFT correspondence, where the defects correspond to one higher dimensional brane that extends into the bulk. Okay, and in this way, knowledge about this object will tell you about spectrum of such branes in string theory. Will also tell you about the interactions on the world volume of this extended branes. So this is a very ambitious kind of set of things that one can think about, but in this limited amount of time, I'll focus on this just this topic, where we'll discuss the symmetries of the quantum field theory in the presence of defects and the kind of universal quantities that one can associate with such system with symmetry, and in particular characterize anomalies. And we'll also see how such anomalies will constrain what kind of defects are admissible in the consistent extended quantum field theory. Okay. I realize there's going to be some overlap between what I'm going to say and what Nadav talked about on Monday, but hopefully there will still be something useful for everyone. Okay, let me just stop for a second if anyone has any question. All right. Yeah, I apologize that somehow from what Matt said, the cursor doesn't seem to be working. So even though I'm trying to point out various parts of the slide, I'm afraid maybe you cannot see it. All right. Anyways, so let's start by reviewing what kind of symmetries there are in quantum field theory with defects. So I want to separate the symmetries into two types. One is intrinsic, the other is extrinsic. They have very different physics. So again, this is the picture you should keep in mind. You have some d-dimensional quantum field theory, and you have some p-dimensional defect, which I denote by curly d, that lives on this world volume, which I denote by sigma. Okay. So here, by intrinsic symmetries, I mean symmetries whose conserved currents is a p-dimensional Noether current that is locally conserved on the defect world volume. Okay, so this is just like the usual symmetries of a local quantum field theory in the corresponding space-time dimension, in this case p dimension. Okay, so this is nothing surprising. What is novel to defects compared to a local quantum field theory is the notion of the extrinsic curvature, extrinsic symmetries. So these are symmetries that are inherited from bulk, and they're extrinsic in the sense that the corresponding Noether current is d-dimensional as opposed to p-dimensional. And the fact that the defect preserves symmetry simply means that the conservation law of this d-dimensional current is preserved even if you insert this defect. Okay, so you should really think about this expectation value as a two-point function that involves the divergence of the current as well as the defect operator insertion, and this has to be 0 in order for the defect to preserve this corresponding symmetry. And this notion, or this kind of word entity, can also be generalized to the case when the symmetry is discrete. The route for this generalization is to use this notion of a topological defect as generalization of symmetry. So in the case of this continuous symmetries, you can define a topological defect, which is this exponential operator defined by some integral over a codimension 1 manifold, where the integrand involve the Hodge dual of the one form built out of the current. And the statement that the defect preserves the symmetry simply means that this operator remains topological even though it intersects non-trivially with the defect world volume. Okay, and once you reformulate symmetries in this fashion, you can generalize this to consider topological defects which are not defined this way but still satisfy the the topological still has the topological property. Okay, for example, discrete symmetries and so on. Okay, So we want to talk about anomalies of these symmetries. So what are some general properties of anomalies before we insert defects? So we know that the anomalies are they correspond to modification of the ward entity for the conserved currents by contact terms. So for example, in 2 dimensions, if you have a U1 current which can develop anomaly of the following form, so you have this conserved divergence of the current can develop a non-trivial contact term when you have another insertion of the current. Okay, and the contact term involves this derivative of delta function, which means that the conservation is obeyed as long as these operators are away from each other, but can be violated at this coincident point. Okay, and anomaly, non-trivial information of anomaly is captured by this coefficient, which is also known as the anomaly coefficient. The same information about anomaly also is captured by anomalous variation of the Panin function of the theory. Again, taking the example of the 2-dimensional theory with U1 symmetry and the current anomaly for this U1 symmetry. In this case, if you couple the symmetry to some U1 gauge field background, which I'll call A, and you perform a gauge transformation parameter of the lambda acting on this logarithm of the Panin function, the anomalous transformation of this guy will capture the same information given here. Okay. And at the same time, the anomaly encodes fine structure of the symmetries. In the case of continuous symmetries, it determines crucially the current algebra, and in the discrete symmetry, it determines the fusion data. So back to this example again, the 2-dimensional U1 symmetry with the chiral anomaly, the same coefficient determines the separated 2-point function, the parity out part of the separated 2-point function of the U1 current as follows. So this is some kind of conformal covariant universal structure, which is not important. What's important is the coefficient is again fixed by the same anomaly coefficient. And generally, if you want to classify what kind of anomalies is possible for a theory with a given symmetry, a strategy you can take is to look for solution to the so-called West-Middle consistency condition, which is a set of consistent condition which must be satisfied by this kind of anomalous variation to take the following form. Okay, and moreover, a kind of lesson we have learned long before and emphasized in recent years is that the anomaly is captured by anomaly inflow from anomaly field theory, which is typically a topological field theory in one higher dimension. Anomalies with these features come with powerful consequences. In particular, anomalies are invariant under symmetric deformations. Okay, so in particular, if you have some RG flow from some UV theory to IR, from some UV quantum field theory to IR quantum field theory, and if the RG flow preserves symmetry, then the corresponding TOF anomaly must be conserved. Okay? It cannot change under this RG flow. This traces back all the way to the argument of Hooft and has been generalized to even general discrete symmetries. Okay? And for that reason, these anomalies are they are universal and robust observables for for theories with those symmetries. Okay, and for the other kind of anomaly, this conformal anomaly, in particular conformal A-type anomaly. Well, in general, conformal anomalies are only well defined when you have conformal symmetry, and among them, the conformal A anomaly has the nice property that they are monotonic under RG. Okay, so as opposed to the nice property of the TOF anomaly, which says they're invariant under RG flow and also invariant under symmetric deformations, the A anomalies are not invariant, but they satisfy the nice monotonic property. Okay, and together this kind of anomaly matching condition for the TOF anomaly and this monotonicity property of the A anomalies, they give rise to very strong constraints on RG flows and on the phase structure of your quantum field theory. And as we'll see, these nice properties will generalize to the case with defects. Okay. The generalization is pretty straightforward for continuous symmetries. For example, the anomalies. So we'll be talking about anomalies for this extrinsic symmetries. The anomaly for the intrinsic symmetry is just like the anomalies of a local quantum field theory with the same space-time dimension as the defect world volume. So here we'll be interested in the anomalies of the extrinsic symmetries. So we'll be talking about anomalies for currents, conserved currents, d-dimensional conserved currents, for example. Okay. So here, such defect anomaly can be in general captured by modification of word entity by contact terms on the defect world volume. Okay, so this delta function schematically localizes the defect world volume, and in terms of these coordinates, it's the delta function that sets all the transverse coordinates yi to 0. Okay, and similarly, this anomalies is also captured by the anomalous variation of the defect binding function. Okay. When you couple the defect to some background gauge field that coupled to this extrinsic curvature, to the extrinsic symmetries, and you perform a gauge transformation on the defect world volume, which are denoted by lambda sigma. And similar to the anomalies in the usual local quantum field theory, they are classified by solution to the Weissenmüller consistency conditions, but for the residual symmetries. Okay. Because the defect breaks part of the space-time symmetries, the non-trivial Weissenmüller consistency condition will come from the symmetries that is preserved by the defect. And then, not surprisingly, this gave rise to more invariant structures, such that those including this delta functions, which is not admissible if you were to classify anomalies for a local quantum field theory. Okay, and as a result, this kind of defect anomalies can be present even if the bulk quantum field theory has no such anomalies. So, for example, odd-dimensional quantum field theory that does not have conformal anomalies or perturbative Hooft anomalies, they can have non-trivial anomalies of such flavors when you have a even-dimensional defect. Okay, as we'll see in examples. And similarly, this defect anomalies also encodes important parts of the current algebra, but now in the presence of a defect insertion. For example, if you consider a surface defect in 3 dimensions, say a conformal surface defect in 3-dimensional conformal field theory, the 2-point function of a conserved current in 3 dimensions that is preserved by the defect can develop an anomaly. And in that case, anomaly denoted by K captures the parity odd part of this 2-point function on the defect. Okay, and here, importantly, the 2-point function is very complicated in the presence of defect. There's a conformal invariant cross ratio here, which denoted by V. But the nice thing is that this whole non-trivial function is completely determined by the anomaly coefficient. And so similar to the anomalies in the local quantum field theory without defects, the defect anomalies are also very powerful in constraining RG flows and the fixed structure of defect, the fixed structure of the defects. Okay, so in particular anomalies are invariant under symmetric deformations on a defect world volume, and they give rise to universal and robust observables for defect theories with those symmetries. And similar to the local quantum field theory case, the Hooft anomalies, they define RG invariance on the defect. Okay, so under some RG flow between UV and IR conformal defects, the Hooft anomalies define RG invariance. On the other hand, there's a notion of a defect conformal A-type anomalies, which define RG monotonic function for the defect. Okay, and together they give rise to non-trivial constraints on defect RG flows. So just to give you an explicit example of what such a defect Hooft anomaly is, let's consider one of the simplest example of a conformal field theory in 3 dimensions, namely the Dirac fermion, a 3D dimensional.
Question. Yes, when you said defect Hooft anomalies are defect invariants, are you talking about RG on the defect, or are you talking about RG in the bulk?
So that's a very good question. If you're talking about just the Hooft anomalies, any symmetric deformation would leave the anomaly invariant. So this includes both defect and bulk deformations, as long as they preserve the symmetry. This has to do with the quantized nature of these Hooft anomalies. This will not be the case for the conformal anomalies. Does that answer your question? For example, for conformal anomaly, you can consider marginal deformation in the bulk. You can consider marginal deformation on the defect. This defect type A anomaly in general is not invariant under marginal deformation in the bulk, even though conformal symmetry is completely preserved. Okay, I hope that answers your question. So just to give an example of this defect Hooft anomaly, let's consider a 3-dimensional Dirac fermion, which has a U1 global symmetry. And let's consider boundary condition for the Dirac fermion that preserves the U1 symmetry and what kind of anomaly it can have. Okay. So from the general discussion, we know that the anomaly, the only admissible anomaly structure takes the following form. So the current, the three-dimensional current can develop an anomaly which can be captured by this kind of contact term, which again is something that localized to defect roll volume. Here is the boundary, and there's some structure that depend on the background gauge field. Okay, and the anomaly is just captured by this coefficient k. Okay. So in this case, there are standard boundary conditions for the direct fermion that preserve the U1 symmetry that can be defined using a projector. Okay? And this allows you to define the, depending on you project the chiral or anti-chiral component of the direct fermion to 0 on the boundary, you have two different boundary conditions that preserve the same U1 symmetry. And it turns out that the explicit computation tells you that this coefficient for the plus and minus boundary condition have opposite Hooft anomalies, and they are captured by the anomaly full-form polynomial, and with a 1/2 coefficient in the front. So you have half of the anomaly compared to a local two-dimensional chiral fermion of plus and minus helicities. Okay, and there are various ways to see the half, but I think I will not have time to explain them. But I just want to show you this very simple example where the anomaly can be understood from Feynman diagram computations. And yeah, right. But then immediate question you can ask is, so this is some free theory, and how do you determine such anomalies for non-trivial defects, which are interacting defects in interacting quantum field theories? And the general strategy to approach such problem is to use the invariant property of these anomalies. So you can compute such anomalies from by turning on deformation in the bulk by changing the theory to some wavy coupled phase where it can compute such anomalies. And because of the robustness of the anomalies, this gives you prediction also at the strongly coupled phase. Okay. Another way to compute such anomalies to use string theory or M theory to study anomaly inflow. And we'll see examples of this in applications. So among all kinds of defects, a special kind of defect are the conformal defects. And these are, this conformal defect describe the critical phase of conformal field theories in the presence of boundaries defects. And they define universality class of defect archie flows. And this defects has the nice property that they preserve conformal symmetry along the defect roll volume, SOP, 2, and sometimes also the transverse rotation symmetry, SOD minus P, inside the full ambient space-time conformal group SOD, 2. Importantly, these defects are distinct from a local quantum field theory of the same space-time dimension because in general, there's no local p-dimensional stress tensor occurrence on the defect roll volume. On the other hand, they give rise to various new conformal theory data, including new critical exponents coming from defect local operators, by Curly S on defect roll volume, and the various defect 1-point function and 2-point function that involve bulk operator as well as defect operators. And all this new conformal field theory data in the presence of defects are constrained together with the bulk OPE data by the so-called defect bootstrap equation, which have been studied in various papers for general dimension, and also shows up in earlier work in 2-dimension as in terms of so-called classifying algebra. Okay. So it just.
Sorry, can I ask a question?
Yeah, sure.
So I mean, from a defect local operator point of view,
yes.
This SOD minus P is like a global symmetry, right?
That's right. Yeah.
Are there any conserved currents with respect to that one on the defect?
No. So again, so this is the extrinsic symmetry. So this is extrinsic in the sense that I introduced in the beginning. All the conserved currents inside this responsible for the SOD, 2 are associated with the stress tensor in D dimensions.
Okay, I see.
Yeah. So in that. That looks like a global symmetry on a defect from the other ones by the fact that they're extrinsic.
Right. Okay. Thanks.
Yeah, no problem. So now that I have introduced, the reason I have introduced the conformal anomalies, conformal defects is because I want to discuss the other type of important anomalies, which are these defect conformal anomalies. So before we talk about defect conformal anomalies, we should first write down what are the word entities for conformal defect. So, so the stress sensor satisfies this word entity in the presence of a defect. The longitudinal components of the stress sensor is conserved because that's the part of a symmetry that's preserved by the defect. But the transverse component of stress sensor is no longer conserved. It develops operator valued contact term where the coefficient is the same as displacement operator. Okay. And the trace of the stress sensor is still zero because the dilatation is part of the symmetry that's preserved by the conformal defect. And now, in the presence of a non-trivial background, for example, a non-trivial metric and also a non-trivial embedding of the conformal defect into the space-time manifold with non-trivial metric, this traceless condition can be modified and corresponding to a trace anomaly or defect conformal anomaly in this case. The general form can be classified by studying the Western window consistency condition, which I mentioned before, and it has been studied by many people. And the complete form takes the following. The complete expression takes the following form. There are several pieces. So this piece is again the delta function localized to defect world volume, and this B coefficient multiplies the Ricci curvature. Is what I'll refer to as the intrinsic defect anomaly. And this anomaly is very much like intrinsic in the sense that it's very much like the C anomaly of a two-dimensional CFT. But you have these other new pieces which are not present for a two-dimensional CFT, which I'll refer to as extrinsic defect anomalies. And these anomalies are new for surface defects. And they are the corresponding invariant structures are built out of the extrinsic curvature, the traceless part of the extrinsic curvature, as well as the pullback of the ambient wall curvature. And this second term is present only if the ambient space-time has dimension bigger or equal to 4, because otherwise the wall curvature vanishes. And this anomalies has various different properties and have been studied in a lot of recent papers. Here I just have a brief summary of their properties. And also to contrast with the properties of the usual C anomaly for local two-dimensional conformal field theory. So first of all, if you look at their origin in the defect CFT data, or CFT data, the C, of course, determines the two-point function of the stress sensor of a local two-dimensional CFT. The origin of the B, on the other hand, determines the two-point function of displacement operator. And it's also known that B1 is the displacement two-point function. D2, on the other hand, determines the one-point function of the stress tensor in the presence of the defect. So the one-point function, so I don't have time to explain, but the one-point function of the stress tensor, bulk stress tensor in the presence of a conformal defect is completely determined up to overall coefficient, and overall coefficient is proportional to D2. On the other hand, right now, even though the two-point function of the stress tensor is satisfy non-trivial constraint, it's still not explicit known how this B coefficient shows up in this two-point function. Although it's certainly expected it's determined by the two-point function, but it's not known how this B, what kind of unique structures here multiplies the coefficient B, for example. Okay. And if you look at their property under RG flows, they also have various different behavior. For example, the C is known to be a monotonic function under bulk RG flow. And similarly, the B function also it was proven by Kristen and Andy that they also satisfy the similar monotonic behavior. On the other hand, the D1 and D2 coefficient do not have such property. That's not surprising because these are extrinsic anomalies and they're not giving some like an intrinsic. They're not giving some counting of intrinsic degrees freedom, so intuitively we don't expect such a monotonic property for this D anomalies. And you can also ask whether this coefficient has any positivity property, whereas for C, because of the way it shows up in the two-point function by reflection positivity, we know that C is positive. On the other hand, again, because B is kind of murky, how B shows up in this two-point function is murky. Relatively, we also don't have any control on the possible positivity property of B. So here, positivity, I should put the question mark, put a quotation mark, because obviously we know B is the examples where B is not positive, but here we also don't know if there's any lower bound on B. Okay. On the other hand, these D coefficients are known to be positive. For example, the D1 is clearly positive by reflection positivity because of the two-point function of displacement operator. On the other hand, D2, it's less obvious to see that D2 is positive, but recently was argued using ANAC that is also positive.
So Yifan, what if you just specialize, I don't know, to interesting classes of theories? I mean, does this general picture ever change? I mean, So I don't know if you have, I don't know, some superconformal defects or something. I don't know,
Right.
some restrictions maybe on what you want to consider. Can
Right.
you prove additional
Right.
interesting things in some of these cases? Or
yes, for example, right, that's a good question. So I have not thought about it, but for example, I think you are suggesting that maybe for superconformal defect, there's some positivity property you can deduce for B. That's possible. I haven't looked at that. The examples I know, right, yeah. So I think you need to have a sufficient amount of supersymmetry to have a positive property. I know that for the high PPS surface defect in virtual pyramidals, the B is positive, but I think that's too special example. Right.
Thanks.
Right, but there are nice things that people have studied in the case of dependence of this anomalies coefficient on bulk and defect marginal couplings when the defect preserves some supersymmetry. For example, it was studied in these papers that the B anomalies cannot depend on bulk marginal couplings if we preserve 0,2 supersymmetry. Okay, but in general, the B can depend on bulk marginal couplings. On the other hand, we also don't have an explicit example of a conformal defect, conformal surface defect that depend on whose B anomaly depend on the bulk marginal couplings. If the marginal coupling in the bulk does not break part of the conformal group. There are some exotic examples where if the bulk marginal coupling also depend on the transverse distance. I think something that study was in another paper of Chris and Itamar. But apart from those exotic examples, we have examples of conformal surface defect where the B does have dependence on bulk marginal couplings. Okay. All right, I think I'm not doing well on time. How much time do I have left?
Yeah, so I guess if we were to leave 5 minutes for questions, let's say you have another roughly 5 minutes before that.
Okay. So let me just let me skip this. So this. Okay, and this is already summarized, so there's some defect RG properties, so let me skip this. So let me just talk briefly about cases where you can extract this conformal defect anomalies in cases where the quantum field theory is interacting, also the defect is interacting. Okay, so this is made possible by studying examples with supersymmetry. So there's superconformal defects. Okay, let me not talk about this. Let me just go directly to this. So the superconformal defect has this nice feature that they preserve when you have enough supersymmetry that's preserved by defect. It has a nice feature that there's some U1 R symmetry or some R symmetry that's also preserved by the conformal defect. And in such a case, you can postulate there could be some relation between the TOF anomaly for the R symmetry and the defect conformal anomaly. Okay, and as I mentioned near the beginning, that this TOF anomaly has a nice feature that they're invariant under symmetric deformations of both bulk and on the defect volume, and they're much easier to access than the defect conformal anomalies. So if there were to be such a relation, you can compute the defect conformal anomalies just by knowing the defect TOF anomalies. And indeed, such a relation can be derived in the presence of supersymmetry, and they take very similar form to the usual relation between conformal anomalies and the TOF anomalies for the local quantum field theory. Okay, and just to illustrate this, let's look at the specific example that is surface defects in the 2,0 theory. Okay, so in this case, the 2,0 theory, for example, the A-type 2,0 theory is engineered by a stack of M5 brains. But there's a general ADE classification of 2,0 theory that are in one-to-one correspondence with ADE Lie algebras. And these theories are known to have large family of half PPS surface defects. I think that's something that I've talked about on Monday. And these defects are generally classified. They're classified by weight vectors lambda associated with the underlying Lie algebra that defines the 2,0 theory. Okay, so for the A-type, this weight vector essentially specifies for the A-type theory, the surface defect can be described by a transfer M2 brane that intersects with the stack of M5s along two longitudinal directions, which is the defect row volume. And in that case, this weight vector lambda specifies before you take the singular limit, how the M2 ends on the M5s, okay, when you separate the M5s. And you can ask in this non-Lagrangian example where you don't have a Lagrangian description for the 6T theory, you also don't have a Lagrangian description for the surface defect, if you can extract anything about the defect anomalies. And the answer is yes. Again, it's made possible by relation between the defect conformal anomaly and the defect Hooft anomaly for certain U1R symmetry preserved by this surface defect. And the way you compute the defect Hooft anomaly in this case, because you don't have a Lagrangian description, is to use anomaly inflow in M theory. And this is also something you can directly do in the field theory from the 2,0 theory. And it was determined by this gentleman that the most general Hooft anomaly, the general Hooft anomaly for all the symmetries, all the global symmetries preserved by the defect takes the following form. It's determined by this anomaly four-form polynomial. And by understanding how this superconformal symmetry embeds, how the U1R symmetry of the superconformal algebra embeds into this the full global symmetry of the defect, you can extract the corresponding U1R defect Hooft anomaly. And then from the anomaly multiply relation, this gives you immediately the defect conformal anomalies for most general half BPS surface defects in any 2,0 theory of APE type. And in the particular case, when the 2,0 theory is of the A type, this agrees with the large N results from that was extracted from holography, and also agrees with the free results. And I think in some early paper of Nadav, and I suppose Nadav also touched upon this point in his talk. Okay, let me, in view of time, let me just end by giving a number of, by outlining a number of open questions. So as I mentioned, that we still don't really have an understanding on what kind of universal bounds or kind of positivity property of the defect conformal anomalies, as well as the all-dimensional analogs of the defect conformal anomalies given by free energy. And one potential avenue is to study bounds that coming from the positive energy conditions, kind of collider-like bound from positive energy conditions. And something I also didn't have time to talk about is the notion of the defect Hooft anomalies for discrete symmetries and even more exotic symmetries coming from topological defects that are not invertible, for example. And there's also this this puzzling feature of odd-dimensional defects. That is, there seems to be, so they don't have any perturbative defect anomaly, but they have the notion, they have a very subtle anomaly associated with the inversion symmetry. For example, the Wilson loop, the Wilson line in inverse preamines, depending on if it's along a straight line or if it's on the grid circle, on the circle, they have different expectation values, and this is already something that's observed in the paper from Drucker and Gross, but it's not understood. It's not this anomaly is still not well understood, and it's also interesting to study something I mentioned in the beginning. Some interesting to study holographic dual of these defects, and whether knowledge about the defect operator algebra that you can extract from the field theory tells you about something on the world volume couplings on these extended branes in the bulk, and similarly, this is related to something I didn't talk about. So there are potential constraints on the spectrum of what kind of defects are admissible coming from anomalies in the quantum field theory. And you can also import those constraints into the string theory or the more general quantum gravity and talk up and induce and deduce non-trivial constraints on what kind of extended branes beyond the BPS branes that are possible in string theory and theory. Let me end here, and thank you for attention.
Okay, thank you very much, Yifan, for the great talk, and also thanks for connecting all the different pieces that we've seen so far in different talks together. That's great, so thank you. Let's see, are there any questions? Yes, so I see Raja. Yes, please.
Hello, so I had a question about the intrinsic defect symmetry.
Yeah.
So in the FFT description of fractal models, we have these subsystem symmetries, right? So yes. Can they be captured by this intrinsic defect symmetry?
So all the discussion here that so you mentioned a very good point. All the discussion here assumes that we have point query symmetry If we do not insist on those, then there are this more exotic symmetries. For example, the subsystem symmetry that you talk about. My personal feeling is that they're kind of similar to the intrinsic symmetry on the defect volume. If you consider a foliation of your spacetime that breaks explicitly, foliation of spacetime, which people discuss in the context of fractal models, it's a bit like just the kind of lattice of defects. And in that case, the subsystem symmetry are just like intrinsic symmetry on the defects. But I'm not sure if this picture would lead to anything that's not known to the fractal people.
Okay, thank you.
Yeah.
Okay, any other questions? So yeah, Nadav. Okay, I was going to actually ask. Go, Nadav, you go, please.
Yeah. So you mentioned the inversion.
Right. Yeah.
And you said that it's true and that it exists in odd dimensions. In even dimensions, is it part of the Euler class anomaly simply, or can it be?
So that's not clear, right? So inversion has this property that it's a large conformal transformation. It's not connected to identity.
Right.
So naively, the usual conformal anomaly is associated with the kind of like perturbative, just like usual perturbative anomaly is associated with perturbative. I mean, something that's detectable just by perturbative transformation. So in that sense, it's different. But I also don't know if this will give you some independent information in the even dimensional defect. Or
yeah,
if
I mean, in the even dimensional one, you still have a difference between plane and sphere.
That's right. So that's what I was trying to say, that if the inversion give you any new information, or it's something that's already captured by the perturbative conformal anomaly, okay, that's not obvious to me.
And no, it's I thought you could have said that because you pointed to it being odd dimensional. I thought you said that it's obvious that there shouldn't be anything extra beyond that. But
oh, okay.
So my question was exactly that. It's not obvious to me that there isn't either. So I think we agree.
Yeah. I mean, for even dimension, at least in the examples where you can actually compute the sphere Penning function and compare, if you in cases where you can actually compute the sphere Penning function, in those cases, I think, well, those are the supersymmetric cases. In those cases, the B anomaly is sufficient to capture the entire non-trivial dependence, right? So at least in those cases, you would say that the potential anomaly associated with inversion probably doesn't carry any more information in those cases.
Yeah. Okay.
But I don't know, like in general, conformal defect in the case, for example, in the case without supersymmetry, where the S2 Penning function doesn't even is not even unambiguous object, right? But the anomaly we think is the unambiguous object.
Mm-hmm.
Right?
Okay, so Charlotte, you have a question, please.
Just very naively, it was again about the same thing in these inversion anomalies for odd dimensional defects. Are there any other examples of odd dimensional defects studied in some detail than the Kruger-Gross case?
I think Nadav's paper studied this Wilson line in, I think it's a very clear example. The Wilson line linked to superpyramid, HPPS Wilson line linked to superpyramidals.
Yeah, no, that's well known, of course. But
yeah,
are there any examples from three-dimensional defects, for instance?
I don't know immediate reference. Maybe some people in the audience, some people in the audience knows. Well, in ABGM theories, I suspect you can do the similar analysis. But I mean, I only know the literature where they compute the Wilson line, like expectation value for the circle.
But wouldn't you say the same thing for the S3 partition function?
Yeah, it's a similar property for the S3 function. Yes.
Yeah. Okay.
So there are examples you can consider Chern-Simons theory, for example.
Yeah. Okay.
Okay, other questions? So I have a question. I guess I could have also asked it to Nadav on Monday if I had been more there mentally. So you also described this ADE classification for 6D SCFTs, and I guess there are these old sort of stringy arguments for it, and then there are kind of more modern arguments based on circle reductions.
That's right. That's right. Yeah.
But those arguments based on circle reductions, I think they're more or less involving local operators. Is there something that you could do maybe with defects from the modern perspective to sort of argue further in favor of this ADE classification?
Yes. Yes, I think that's a very good question, but that's a very good question. So in 2,0 theory, I think what you're imagining that there could be distinct 2,0 theory that with the different spectrum of surface defects.
Yeah, for example.
Yeah. Very, very similar to what happens in the 40 gauge theory. But in the 40 gauge theory, there are this theta angle, which is the discrete theta angle, which is closely related to the spectrum of surface. The line defects. But I don't know such a thing in 2,0 theory. So it's not. Yeah, I think it's a very good question, but yeah, I don't have anything intelligent to say about it at the moment. So I think you can try to. Yeah, I don't know if you can uplift. You can first go to the 4-dimension and try to uplift. But all of them would involve insertion of additional defects when you do computation, right? You need to kind of this automorphism twist to get this other 4-dimensional theories.
Right.
So it's not just about surface defects.
Yeah.
It's a very good question. Yeah.
Okay, any other questions? If not, I believe we're going to have a discussion session. I will probably not be there, but I believe some non-zero number of organizers will be there. Yeah, any last question before we adjourn?
Maybe I can ask one more.
Yeah, go ahead, Raja. Yeah.
So for topological defects, we have this description in terms of higher categories.
Yeah.
So for more general defects, at least for subclass like conformal defects, is there some idea of the capture?
Yeah, there are module categories.
I see.
There are module categories of your higher categories. Yeah. For example, this is something that I think people in the audience have studied. I think maybe Jared. And so in the 2-dimensional context, the boundaries, the conformal boundaries. So in 2-dimensional context, you have this topological defects in the bulk, topological lines. They give rise to some fusion category, right? And in that case, the boundaries correspond to a module category for the fusion category.
Right.
And this structure generalized to higher categories when you go to higher dimensions.
I see. Okay. Thanks.
Okay, great. Okay, so I don't see any more hands up. So let's thank Yifan again for a great talk. Thank you.
Thank you.
And, maybe we shall end the recording.